All right, welcome back to Chapter 12. I'm going to finish up reductions here. This should be a pretty short video. Reductions of CX bonds. So we're going to look at section 12.6. Reduction of polar CX sigma bonds. So alkyl halides and epoxides is what we're looking at. Okay. So Rx, we can treat with this reagent lithium, aluminum hydride, and H2O. And go over mechanisms, and we get a substitution reaction. We'll see this is just SN2. It's SN2 with a new nucleophile. And then epoxides, similar to what we've talked about, are going to undergo SN2, but at the less substituted carbon, same conditions, lithium aluminum hydride, H2O. We'll see that we get something like this. That's the H coming from the hydride. Get these two main reactions. Okay, so we're going to see, we'll talk about what lithium aluminum hydride is. We're going to see these two main reactions. So let's show real quick what lithium aluminum hydride means. Lithium plus with an aluminum hydride, tetrahydride technically. There's a negative formal charge on aluminum, and this reagent is very similar to sodium borohydride. Okay, we've talked a lot about boron. With 3 bonds on it has an empty p orbital, but boron with 4 bonds is tetrahedral. We've talked about 4 bonds less. Okay, and so lithium aluminum hydride, sodium hydride over here is like a hammer. And if that's a hammer, then this is a sledgehammer. You don't have to know that, obviously. It's just to try to give you a qualitative difference. Lithium aluminum hydride is much more reactive. There's a lot that goes into that. It's the identity of the metals involved. And but in any event, I want you to understand these 4 bonds to both of these atoms, aluminum or boron. Both of these are sp3 hybridized and tetrahedral in nature. And these are both an equivalent of hydrides. But in contrast to sodium hydride, which we've seen before, these are going to be nucleophiles primarily. The identity of them is such that they act as nucleophiles more so than bases. They can act as Bronsted bases. But we said that sodium hydride here is just a base. It's a non-nucleophilic base for electronic reasons. These are nucleophiles primarily. They're borohydrides. They're aluminum hydrides, not just hydrides, not just metal hydrides. So let's go over the mechanisms. We have an alkyl halide, and we're going to add lithium aluminum hydride. Little I, double little I just means it's sequential. We are substituting. We're replacing chlorine for an H, right? SN2 substitution. Here's the mechanism. This attacks just like an OH minus or something like that, but it's the pair of electrons in this bond and the hydrogen are attacking this bond and doing SN2. That's all the mechanism is. 2 arrows. Okay, for this part. So that takes you to product, but what I want you to see is the byproduct. And I want you to show this as well, right? Just like BH3, aluminum alane, we call this, AlH3, has an empty p orbital. What have we generated? We've got a Cl minus and a lithium plus, well, this is a very reactive Lewis acid, the aluminum. Chloride is going to attack that and give you this byproduct. And they're still ionically charged and stabilized, so you get this lithium aluminum anion. Okay? Again, the formal charge is on aluminum, but there is no lone pairs there. Aluminum is not negative. It's the whole complex that is negative. It's formally on aluminum. Okay? So that's the mechanism. Let's go over bromide, lithium, aluminum hydride, H2O. What do we get? New H. So you gotta show that H there. What's our byproduct? That. Okay, very similar, just a bromide instead of a chloride. So let's take a look at epoxides. The same rules are going to apply. We have a strong basic nucleophile, so we have to choose between two positions on the epoxide. Lithium aluminum hydride and then water. We're going to add excess. And I should note, the water, you always add water to lithium aluminum hydride because it's a very reactive species. So in the first reaction with the reduction of the alkyl chlorides, the water is simply quenching the lithium aluminum hydride, so it doesn't come into play mechanistically. Here it does. Okay, so let's follow this through. What's going to happen in this mechanism? Here's our lithium aluminum hydride. What's going to happen? These electrons are going to attack the less substituted carbon. Okay, popping open. This is step one. Popping open the ring. Okay, and we want to account for our charges. This is one thing the book talks about. It's another sort of, I think, abbreviated mechanism that I don't particularly like. And we're going to add a step to the mechanism because it's true, you get this sort of O minus, but instantly it's going to interact with AlH3 in the same way that the chloride did. This O minus is going to attack, and what's going to happen is it's going to form an oxygen aluminum bond as an intermediate. And there's the lithium. Okay, so that's going to happen pretty quickly. And then water, we don't need to show it. We're going to skip this step. I'm happy to go over it if we want to. It's multi-step way of explaining it. You can use this abbreviation. You are going to replace this whole group with an OH, right? And you're going to take the H from water and put it on there. So that H that's circled is from the hydride. This H that is squared is from water. Okay, so we can go over that in class. I won't make you draw that. You can just say this part right here. You should draw the byproduct. Okay, but that's the that's where it comes from. So a hydride comes from lithium aluminum hydride. A proton, an H plus, essentially comes from H2O. Okay. So let's look at a couple more examples of epoxides. Single enantiomer. Okay, this stereocenter over here is simply sort of an observing stereocenter. Not observing, but it's just not going to change, whereas the epoxide stereocenters can change, right? Lithium aluminum hydride is going to come from the front face, in this case, the backside relative to the oxygen. It's going to attack from the front of this molecule, the H is going to sort of attack like that. You push that out. And after protonation, what do you get? You get an alcohol. And we don't have to show both of these, but the H from the hydride came from the front face. So if we circle the one that came from there, and then that methyl group is still there. So you get a single enantiomer starting material going to a single enantiomer product. Okay? Take home would be good to do is if you replace all those H's with D's, where would the D be? Do this problem with lithium aluminum deuteride, and that would give you the D over here. Okay, to kind of trace that D through there. One point to make about these lithium aluminum hydride reagents is that they do not reduce double bonds. Right over here on the right we have a double bond. It doesn't get reduced like it would with H2. What does happen? You reduce epoxides or alkyl chlorides. So lithium aluminum hydride is going to come from over here. It's going to open up at the less sterically hindered position to give an alcohol after protonation, and again the H from the lithium aluminum hydride came from the front face. Okay? So you get that product, and that's reduction. Okay, so we're done with reduction. What did we talk about? We talked about hydrogenation of alkenes, we talked about hydrogenation of alkynes, and then some other ways to make cis alkynes with Lindlar catalyst, and then to make trans alkynes with dissolving metal reduction, so not hydrogenation. You can make trans alkenes. Okay, so you can take alkynes and you can make cis alkenes with Lindlar, or you can make trans alkenes with dissolving metal reduction. And then this lecture we talked about lithium aluminum hydride as a useful reducing agent as a hydride source, reducing alkyl chlorides or bromides, alkyl halides, and opening epoxides, much like the epoxide opening reactions that we talked about back in Chapter 9. Okay, so that's the end of reduction. We'll do some more videos on oxidation.